Hi everyone, my name is Shao-Chieh. Today I would like to talk about our open source software senior design project, camera-based car speed detection library for autonomous vehicle at Purdue University. I am the software architect and the team leader of this team, and I am in charge of developing the library and also the documentation. Christopher is in charge of generating training data using Carla Simulator for us to train our model. Meenakshi is in charge of writing a research paper to document our finding in this project for research purpose. Since the rise of Tesla, vehicle manufacturers realized that autonomous vehicle is the future. Manufacturers like Honda and Toyota are transferring their cars to autonomous driving. Lots of car equipment are being transferred from the traditional hardware-based to software-based equipment like the speedometers, which is the main focus of our project. The reason that software-based equipment is preferred is that it will be more adaptive to different types of cars and will not only be limited to certain hardware. There are two existing solutions for car speed detection these days. The high-cost LiDAR that is used by Waymo from Google with high accuracy versus low-cost camera used by Tesla, AI, or Mobileye. For our solution, we choose to use the video streamed from the dashboard camera combined with the machine learning and image processing technique we developed to detect the speed of the car. Our goal is to develop a car speed detection library on PyPI that provides pre-processing, training, and speed detecting functions that allow developers to use our library to train their own model based on their needs. So why would we choose camera-based speedometers? The most direct answer is of course the low cost of dashboard camera compared to LiDAR. But the most important reason for us is that we believe that with the image processing and AI technique these days, anything that could be seen, processed, and understood by human eyes, a camera with good AI algorithm could also do it. This is our belief and our vision. Here is a short clip of the car speed detected by our library using the optical flow algorithm on the bottom right corner. It can be seen that there isn't too much difference between the actual speed and the detected speed because of our outstanding library performance. For the system architecture, there are 5 modules that are mainly used in our library. For data analysis, we use NumPy, Pandas, and Matplot to access, analyze, and store the data. We choose OpenCV to process the video, including calculating the optical flow of each frame, resize and slice the velocity metrics we acquired from the optical flow algorithm. The optical flow is the secret sauce of our library that we use to extract the movement of objects between 2 frames, which allow us to use this kind of information to train our artificial neural network model, also known as ANN model. We later use the Keras model provided by TensorFlow to train the ANN model and detect the speed of the car. We have also plotted the data flow diagram in order to analyze the security of our library. As can be seen, we choose the library that are well developed, stable, and secure to reduce the security issue that might arise. We also highlighted the places that might be targeted by the adversaries with bright yellow color, and suggest developers to use the security method they preferred to protect the database. For documentation, we use Sphinx to generate documentation and publish it on readthedoc.io automatically as our CI on our Github repository. It could make sure that every time there is a push into our main branch of our Github repository, the documentation will also be updated, so it will always be in the newest version. The graph on your right-hand side is a screenshot of our documentation on readthedoc.io. We provided the project description, API, training data, and model, example code, and Q&A in our documentation. We wish it could help developers to quickly pick up our library without encountering too much issues. For licensing, we first use CycloneDX to generate the software bill of material, SBOM, of our library for two reasons. Firstly, we want to make our library totally transparent by providing the information of what our library is consisted of. Users could examine the software bill of material to ensure that the library we included and its root library are all secure and could meet their requirement. The SBOM also helps us decide which license we want to choose. Given that most of the libraries in our SBOM are either MIT or Apache 2 licensed, we choose MIT license for our library, so it could meet all the legal requirements and still be open sourced. For the release, we choose the conventional semantic versioning scheme for our release on PyPI. After the release of our midterm beta artifact version 0.7, there has been 9 releases until now. Before April 24, 2021, our library was still unstable, and we totally found 8 bugs based on beta users' feedback and fixed them. On April 26, 2021, we released stable version 1.7.0 on PyPI. It is the first stable version of our car speed detection library that has been released, and there are totally 7 features in our library. For our final release, version 1.7 on PyPI and readerdoc.io, we have met all 5 smart requirements that we proposed on our final proposal. For the first requirement, we propose to develop a pre-processing pipeline that could assist the CNN network to produce a good result. The output of the pre-processing pipeline could be visualized through a function code. It could be measured with a mean square error less than 10 for our speed detection library. To verify that we meet this requirement, we use the training video provided by Comma AI to test our model. The ANN model generated from our library successfully achieved mean square error less than 2. It means that the speed of the car we detected using our library are only plus or minus 2 km per hour away from the true speed. We also outputted the velocity metrics from the preprocessing function so that the user could, based on their need, to visualize the result. Please note that on our documentation, we use the term artificial neural network, ANN, instead of convolutional neural network, CNN. ANN is a more strict definition of CNN. The main difference between ANN and CNN is that ANN requires each layer in the neural network to be fully connected, while CNN don't. So ANN is part of the CNN. So for our smart requirement first, our first smart requirement is done, is checked. Our second requirement would be to design a CNN or ANN module that can detect a car speed by the dashboard camera. It will be measured with mean square error less than 10. Like I have said before, we have successfully designed the model using ANN, which is a more strict version of CNN that could detect the speed of the car with mean square error less than 2. So smart requirement 2, check. The smart requirement would be the third smart requirement would be to package the module into a library and publish it to PyPI. We have successfully published the version 1.7 stable version on PyPI. The link could be seen on the left side. Smart requirement 3, check. The fourth smart requirement would be to provide a well-documented API included Q&A. Not only we provided the documentation of API and Q&A on readerdoc.io, we also provide project description, example code, and training data on it. Double check. The fifth smart requirement would be to provide a well-documented record of our development process and summarize our finding in a brief report and provide suggestions for future researchers. We have included all this information in our final project archive, and it will be published on readthedoc.io as well. Check. For bonus, our team member Christopher has generated 150 minutes of training video using Carla Simulator on 3 different maps: city map, rural map, and highway map. It gives users a more diverse data to train their model. Later, Christopher will share his development experience of generating data from the brand new car simulator. Another bonus of our project, our team member Meenakshi has written a research paper to document our finding and are ready to publish our paper on the AI conference. We are happy that we could not only contribute our project to the open source community, but also the academy research area. Later, Meenakshi is also going to share about her development experience of writing a research paper from scratch. So, let's hear about their experience.
Hi, my name is Christopher Crocker, and this is my presentation. I will be discussing my role in the project. I did the data generation section, and I will be discussing that. I'll be discussing my experience with doing that, and I will be discussing how I believe the outcome went. So, data generation. I generated data using the Carla Autonomous Driving Simulator. I recorded the videos using a camera that I placed inside of the virtual car as a dash cam. I used the geographic information system technique to generate lots of high quality data while doing it on a relatively small number of maps. My experience with my part of the project was largely just an experience with Carla. And my main experience was that I discovered that Carla, while relatively easy to use and program for, it had extreme hardware requirements. My GPU and CPU are both very powerful, but I was only able to achieve 30-40 frames most of the time. And that was largely because the simulator is not properly threaded for the CPU. It only used roughly 25% of my whole CPU at any given time. I also discovered that recording the video required too much CPU, and so what I did was I just saved the raw data onto the disk, which used an extreme amount of disk usage, roughly 375 megabytes per second. I also discovered that the simulator is not very consistent with its frame rates. I was able to get around that using the constant time step mode, which was pretty simple. However, I also discovered that the simulator would skip a whole lot of frames, which was also a problem. However, a bunch of tweaking, I was able to get it to only 0.2% of frames were skipped, which I believe was pretty good. Finally, the outcome of my section of the project was that I generated 2.5 hours of data across 3 maps and 12 videos. And I also wrote the 1 page of the paper, which was the data generation section, explaining my methodology for generating the data. Thank you.
Hello, my name is Meenakshi Pavitran, and this is my senior design final presentation. I'll be talking about the big picture of my role in this project, my development experience, as well as the outcome. Starting off with the big picture, I wrote a research paper on our model that detects the speed of a car through video streams. We intend to publish this paper on arXiv and/or research conferences. Since the paper contained a detailed account of our solution, I was dealing with the documentation part of our senior design project. I had written the following sections as mentioned in the slide, that is the abstract, introduction, related work, etc., etc. I had written about the need for the solution, compared our solution with the previously existing solution, described preprocessing the data for our model, and described the model itself as well as the results obtained in detail. The problems I faced along the way was that I had to learn how to write a paper. I solved this problem by reading other research papers to become familiar with them and the language they used. Another problem was having to carefully choose any sentence I would have to write, since I would need to have citations for any claim I make. I also needed to be familiar with both the model and the data generation in order to write the paper. I learned a lot as part of the senior design project. I learned to work in a team since I had to communicate and collaborate with my other team members in order to perform my role well. Moreover, I learned a lot about computer vision from the papers I read, as well as to our own model that we had built. I also learned to document and write a research paper. I had to have effective and steady communication with my team members on a regular basis in order to understand their work and what they were doing so I can document it in the research paper. Finally, the outcome of my role in the senior design project is that I have the final draft of the research paper and it is ready to be reviewed and submitted to a research conference and/or archive.
Thanks for Christopher and Meenakshi for sharing about their development experience. Now I would like to demonstrate our library and also our documentation. Okay, now we are at our GitHub repository of car speed detection library. The source code are provided all over here, and we are going to scroll down and you can see the README. In the getting started, we will provide instruction for how to pip install our library. And if I click this link, it will direct us to the car speed detection library. It is in the 1.7 stable version right now. And you could see all the instruction below. Now let's go back to our repository. One of the most important thing about library is its documentation. So let's click the link and go to our documentation. All of these link documentation are auto-documented by Sphinx and CI to readthedoc.io. Now let's click our About first. Here is our project description. For the API, these are auto-generated by Sphinx, and you could learn how to use our library, what method each function would take in and return. For data and links, we provide all of the training video we produced using Carla Simulator, and the corresponding model we trained with it. We also provide the model we trained using the training video provided by Comma AI. You could also find the SBOM here. We also provide the Q&A section with the most common question that our beta user often asks us. And if you have more questions, you could also contact Shao-Chieh Lian, which is me, at lianshaochieh@gmail.com. Okay, let's go to the example code. In our example code, there are actually only 5 lines of code that you need to write. Pretty amazing, isn't it? Now let's check our code line by line. First of all, we include our library, and then we read the training video and output it frame by frame into a car detection image directory. We then preprocess all of the images that we have stored inside the car detection images, along with the training speed data, and we will output it into a feature text. We will also provide the parameters of resize slicing that allow user to, based on their needs, to slice the metrics. Now we could train our model using the feature.txt. And then now we could use the model we acquired from the training function, and along with the testing video we want to test, and output the speed we detected into the detected result.txt. Now we could combine the testing video with the detected speed and output it into a new MP4 file. Now let's copy our example code and copy-paste it on the Google Colab. We also need to include the pip install of our car speed detection library. Now we have finished installing our library. I have also included the training video provided by Comma AI. The training video and the model we trained could also be found on our documentation and readthedoc.io. For the reading and preprocessing function, it will take around 10 minutes for it to process a 20 minutes long training video. Now the program is running the training function. Note that we split the data into 75% for training and 25% for testing. The testing dataset will only be used for testing, so our result will be fair and accurate. Our library will automatically test the model we just trained with the testing set, and you can see that the result is MSE equal to 1.25, which means that the detected speed using our model is around plus or minus 1 km per hour away from the real car speed. After we confirm that our ANN model is good, we will use it to detect the speed of test.mp4, and the result will be output into a new mp4 file. Let's open it now. As can be seen, the speed of the car detected using the model we just trained has been printed on each frame, and you can see the car is indeed getting slower from the speed printed. Pretty cool, isn't it? This will be the end of our demonstration. For our project future, we have set up 3 missions for ourselves. The first mission is to publish our paper on research conference to contribute to the academy research. Our second mission is to generate more data using Carla Simulator so that we could benefit the users of our car speed detection library and the community. Our third mission is to manage our library regularly and support bug fix for at least 2 years. Here is some link to our work. The first link is the Github Repository of our car speed detection library. It is totally open sourced. It also met the first and second requirement, smart requirements, that I have mentioned before. The second link is a PyPI of our car speed detection library. It met our first, second, and third smart requirements. The third link is to the documentation of our car speed detection library on readthedoc.io. The fourth link is to the GitHub repository of our data generator using Carla Simulator. For the fifth link, we will share about it after our paper has been published successfully on the conference. Thank you for listening to our presentation. If you have any question about our library or want to contribute to our project, feel free to contact me at Shao-Chieh@gmail.com. Thank you.